All right. Good morning, good afternoon, and good evening to all of you for joining us from different parts of the world. We are sorry for the delay. We have some technical hitches. That's how come we couldn't start exactly on time. But we are so grateful for staying with us to the full webinar. Welcome to our webinar on mapping the plastics. I would like to know if you can hear me clearly. Simon, are you able to hear me?
So I can hear you. Can you hear me?
Great, I can hear you, Simon. All right, so I'll go ahead. We appreciate you taking time with us today. While we wait for a few more participants to join, feel free to introduce yourselves and your organizations in the chat box. We will start shortly. So we will be grateful if you could introduce yourselves in the chat box whilst we start. So whilst we do that, I would like to say that Geospatial Environment Resources Working Group of the Ghana Geospatial Society is delighted to welcome you to today's webinar on mapping the plastics. I am Gameli Komla Agwada. I will be your moderator for this evening. And the purpose of today's webinar is to bring together geospatial professionals who are passionate about addressing the global plastic waste crisis. Through our collective expertise, we aim to explore innovative mapping techniques and strategies to help communities effectively manage and mitigate plastic pollution. So to provide you with a bit of a background, I would like to invite Mr. Kwame Boateng, the secretary of our working group, to share more about the Geospatial Environmental Resources Working Group. Kwame, kindly come on board. Okay, whilst we wait on Kwame, I could see that participants are introducing themselves. Welcome with Wilson Baku. We also have Yasser Arafat of Ghana, Nanton District. We do have Samuel also Kofi with us. We have Alex Nathan Akwe, who works with the Lands Commission. We have Sintiche. Sorry if I'm not able to pronounce your name correctly. Sintiche Boafuate with Newmont Africa. Jesilabi Ado Kwehua from Plains, North Donkokrum. He is a district fiscal planning officer. We do have Prosper Kwame Detono with Land Use and Spatial Planning Authority, LUSPA. So Kwame, please come in if you are.
All right, Gamali.
All right.
Thank you so much. Thank you so much. And thank everyone for joining us today. This is one of the working groups of Ghana Geospatial, as mentioned earlier. And then we are called the Geospatial Environmental Resource Working Group. And what we are mainly focused on is to establish, we actually established to facilitate our collective effort. The idea is we want to promote sustainable management of environmental resources. Now, we focus mainly on leveraging geospatial technologies, to address these challenges that are related to our environment, such as waste management. We are also interested in environmental conservation and then climate resilience issues. This year, we aim to enhance these collaborative endeavors that we are putting together for the sustainable management of environmental resource. And we want to do this through engaging like webinars, informative presentations, and interactive seminars. And today's webinar is one of such efforts. We believe that this session will serve to expand our members' understanding and further the promotion of a secure and a sustainable environment. And we are happy to have everyone on board. Thank you for joining us once again. and we hope you have a very fruitful session. Thank you.
All right, thank you very much, Kwame. Now let's have some few housekeeping rules. So before we dive into the presentation, this webinar is supposed to last for approximately 2 hours. It might be less. Please introduce yourself and your organization in the chat box if you haven't already. As I can see, we have people introducing themselves. We see it as an opportunity to network as well. Kindly also keep your phones or microphones muted throughout the webinar to minimize background noise. And also, if you have any questions or comments, please use the chat box. The moderating team, Veronica, Kwame, and myself, read them out during the question and answer session at the end. So without much ado, I'd like to pass on to our chair for the working group, Madam Nadide Tego, who would introduce our presenter for today. Thank you very much.
Thank you, Gamali. It is my pleasure to introduce Mr. Simon Ironside, a highly accomplished surveyor based in Christchurch, New Zealand. Simon is a licensed cadastral surveyor and the Level 1 certified hydrographic surveyor with extensive expertise across both fields. Currently, he serves as a senior cadastral surveyor with the Land Information New Zealand, where he plays a critical role in mentoring the staff and ensuring the quality of cadastral survey datasets. Before joining his current workplace, Simon made significant impact in the private sector, particularly following the Christchurch earthquake of 2010 to 2011, which stands as one of his most rewarding chapters in his career. In fact, beyond New Zealand, his career has taken him around the world. He has worked in the United Kingdom, Libya, Jordan, Iran, Nigeria, and across Southeast Asia, supporting advanced technology with Trimble. A fellow of the New Zealand Institute of Surveyors, Simon has contributed actively to the international surveying community, particularly with the International Federation of Surveyors, which is known as FIG. He was the co-conference director for the FIG Working Week of 2016 in Christchurch, and he continues to work hard with the Commission 4. Currently, he is the co-chair of the Working Group 4.3 on mapping the plastic and serves on the FIG Climate Compass Task Force, reflecting his deep commitment to environmental challenges. In this webinar, Simon is going to walk us through the inspiring work of the FIG Commission 4.3, that's the mapping the plastic, for work they are doing on global plastic pollution. Help me, let's invite Simon Ironside to make his presentation. Thank you.
Thank you now. Without further ado, Mr. Simon Ironside, the floor is yours. You have up to 40 minutes for your presentation. Thank you.
Thank you very much, everybody. I'll just share my screen to start with. Can everyone see my screen?
Yes, it's
You can
visible.
see? Okay, thank you very much. Good evening to the Ghana Geospatial Society. Thank you very much for inviting me to give this presentation. I was in your beautiful country in May at the FIG Working Week that was held in Accra, and got to know several of you there. Also others who I have known through FIG for a number of years. So yes, it's very nice to be able to give this presentation again. So this is what we gave in Accra for our presentation. So I will start it if that's okay. Hang on, I will just. This FIG asks us each commission to map the work it is doing against the UN Sustainable Development Goals. And for Commission 4 in mapping the plastic, this involves SDG 6, which is clean water and sanitation, SDG 13, which is climate action, SDG 14, which is life below water, and SDG 17, partnerships for the goals. The New Zealand journalist Gordon Campbell wrote recently that compared to COVID and climate change, the threat from plastics seems like a low-rent version of planetary disaster. Is it possible that the single-use plastic bottle, the fast food plastic knife and fork, or the plastic packaging wrapped around virtually everything we consume are really omens of the apocalypse? The answer, unfortunately, is yes. The effects of plastic pollution on the Earth's oceans are well documented, potentially catastrophic, and increasing exponentially year on year. UN estimates suggest that more than 75% of all the plastic produced since 1950 is now waste, with the majority of it discarded into landfills or dumped into marine environments. The UN Environment Programme has conservatively calculated that each year more than 8 million tons of plastic ends up in the oceans. That is roughly 15 tons of plastic entering our oceans every minute. And 80% of all litter in our oceans is now made of plastic. And without action, the World Wildlife Fund for Nature estimates that by 2050, there will be more plastic in the sea than fish by weight. Only 9% of plastic waste is recycled. It is difficult to recycle, slow to decay, expensive and polluting to burn, and breaks down into microplastics, particles smaller than 4.75 millimeters in diameter, that enter the food chain and cause harm to animals and potentially to humans. We've all seen the images of fish and seabirds choking on plastic, but that, unfortunately, is just the tip of the iceberg. Microplastics are present in the clothes we wear, the water we drink, and throughout the food chain. An estimated 14 million tons of them reside on the sea floor. The UN Environment Programme estimates that just 10 major river systems carry more than 80% of the plastic waste that ends up in the Earth's oceans, with 8 of them in Asia. This is the graphical representation of where a lot of this waste is coming from for these rivers. However, Schmidt, Krauth, and Wagner note that while ocean plastic remains a daunting problem, this could be good news for the quest to control it. A relatively few river catchments contributing to the vast majority of the total load implies that better waste management practices and other potential mitigation measures could be highly efficient when applied to high-load rivers. The authors suggest that reducing plastic loads by 50% in the top 10 ranked rivers would reduce the total river-based load to the sea by about 45%. This slide is from the Commonwealth Scientific and Industrial Research Organisation of Australia, and illustrates the waste transportation pathway and is from research undertaken in the Bay of Bengal at the outfall of the Meghna, Brahmaputra, and Ganges river systems. Plastic pollution of our oceans is an intolerable problem that needs immediate and far-reaching action to remedy. Eric Solheim, the former head of UN Environment, speaking at the launch of the Clean Seas campaign in 2017, argued that it is past time to tackle the plastic pollution problem that blights our oceans. We've stood by too long as the problem has gotten worse, he said. It must stop. FIG and the surveying and spatial sciences profession agree. Mapping the Plastic Working Group is a combined initiative of the FIG Young Surveyors Network and Commission 4, which is hydrography. And it was formed as FIG's response to the plastic pollution crisis. The question, of course, is how surveyors and spatial science professionals could best contribute to the global battle against plastic pollution, given our specific remote sensing, hydrographic surveying, project management, and overall measurement science skill sets. Remote sensing data combined with artificial intelligence algorithms and GIS tools has the potential to overcome current plastic mapping limitations and provide a long-term and resource-efficient solution to the mapping and monitoring of floating plastic waste. UAV orthophotos can provide suitably accurate data for the mapping of floating plastic, but most techniques rely on visual interpretation and manual labeling. So in considering these limitations, we were wondering whether deep learning algorithms could be the solution to extracting floating plastic waste from UAV orthophotos, enabling the differentiation of plastic types and determining the relationship between spatial resolution and detectable plastic size. 2 study areas were chosen in Bosnia and Herzegovina, where some of our working group members are working. The first was a clear, non-polluted, deep water lake, Lake Balkana. And the second study area was situated at the confluence of the Krna and Rika rivers, which unfortunately are polluted. A net for collecting the floating plastic waste was installed. The net was surveyed to test the algorithm's ability to differentiate between plastic and non-plastic. Wooden frames of thin transparent gauze were used as targets together with polyethylene PET. It's a big word. Bottles of varying size and color connected by nylon rope. Plastic squares of orientated OPS or polystyrene with side lengths of 1 to 10 centimeters were attached to the first frame shown figure B. The second frame contained plastic squares with side lengths from 11 to 16 centimeters attached to a metal frame 20 centimeters underneath it, consisting of the same transparent gauze with plastic squares attached with side lengths from 1 to 10 centimeters shown A.
All right, Simon.
Yes.
Sorry to cut in. Do you mind turning on your camera?
My camera, yeah.
All right. Thank you.
No.
Do you mind?
Yes.
Great. We can see you. Thank you.
You can
Please
see
go
me.
ahead.
Okay. Okay, no problem. The plastic in the target frames in study area 1 and the plastic waste contained by the net study area 2 was surveyed using a DJI Mavic Pro UAV equipped with an RGB camera and RTK GNSS at differing flying heights to determine the optimum ratio of flying height to resolution. The flying height and spatial resolutions are shown here, and I will come back to them, but effectively our studies have shown that for optimum resolution, which is 4 millimeters, a flying height of 12 meters was found to be the optimum height, although we flew at several other heights to work out what the best resolution could be gained from. We have successfully extracted floating plastic and land-based plastic from high-resolution orthophotos using deep learning semantic segmentation algorithms, which assigns a set of predefined class labels for each pixel in the image. This is how we do it. For each flight, the acquired images and the structure for motion algorithms are used to generate a high-resolution orthophoto. Deep learning algorithms need to be trained using ground truth data. However, as this was the first attempt to map plastic, ground truth floating plastic data was not available. Pixel classes had to be manually delineated and labeled. This presented some challenges due to the small size, the differing colors, the different spectral signatures, different level of submersion, and constant movement of the floating plastic pieces. To reduce the errors caused by manual class delineation, the multi-resolution segmentation algorithm in Trimble's eCognition software was used to merge the pixels to obtain meaningful non-overlapping objects and polygons. Each segment was then manually labeled and classified using QGIS software based on the visual inspection of the orthophoto. The networks were trained using using Google Colab. The first study area, the floating plastic, was classified into three plastic classes: PET, OPS, and nylon. In the second study area, plastic was classified as either plastic or maybe plastic. End-to-end semantic segmentation model is used for floating plastic classification. It is based on the UNet deep learning architecture. UNet architecture has been widely used for semantic segmentation of remote sensing imagery and can provide precise segmentation with very little training data. UNet has a symmetrical encoder-decoder architecture. Each model encodes and then decodes a feature map to assign a classification result to each pixel of the input image. Of the 4 different architecture models used for the extraction of the different plastic classifications, the ResUnet 50 architecture had the highest detection accuracy for the 3 plastic classes tested. It was found to be the most sensitive to detecting small differences in the amount of reflective energy, which is crucially important for plastic detection and different plastic types. The other models were discarded, and all the subsequent processing was undertaken using the ResUnet 50 algorithm. This is a slide showing the process flow that was used. And this is the ResUnet 50 deep learning architecture. With each model encodes and then decodes a feature map to assign a classification result to each pixel in the input image. Classification results using the ResUnet 50 algorithm compared to the ground truth data is shown here. The visual comparison at different spatial resolutions and for different plastic materials located underwater at A and on the surface B, C, and D. The results indicate that orthophotos with 4mm spatial resolution can be used for plastic surveys using the CSIRO International Marine Litter Classification Standard, which requires a 1 centimeter squared minimum detectable plastic size. While 18mm spatial resolution can be used for debris surveys using OSPAR, NOAA, and UNEP IOC guidelines requiring a 2.5 centimeter squared minimum plastic size. The algorithm achieved high precision and low recall values, indicating that the model could not detect all plastic pixels, but it could be trusted when it did. Visual comparison between the orthophoto, ground truth data, and classification results for the 5 different scenarios at study area 2 are shown here. A is the group plastic. B is a single plastic item. C is the plastic in shallow water. D are the training data errors, the orange lines, which were misclassified by the operator and correctly classified by the algorithm, which was very encouraging. And E was plastic on the ground. Now, when we first started this, these tests and this study program, we hadn't expected to be able to detect plastic on the ground as well as we did, which opened up a whole new area for us. So not only have we got to the point where we can detect plastic that's just floating and slightly submerged, but we can also detect plastic on the ground through this process, which we had not set out to do to start with. The algorithm detected plastic accurately in shallow water and accurately extracted the plastic pieces that were omitted from the training data, demonstrating good generalization abilities. The model also proved its potential for plastic detection on land as well as water, as I've just mentioned. Here are some more examples on the left and the right, showing what the algorithm has detected from the actual photos themselves. And here again is some more. So now we turn to Ghana, which unfortunately has a problem which is severely affecting communities. This photo is an old photo, but was taken at Korligono Beach in Accra in the aftermath of a severe storm in 2016. Much of the plastic waste was flushed out to sea via the storm drains and washed up on the beach by the tides and the currents. Unfortunately, some more confronting statistics, this time based in Ghana. This is an image I found online by some activists who were protesting against single-use plastic. Everyone I talk to in Ghana is very aware and very critical of the plastic waste problem, and the government, to their credit, has decided to act. In 2019, it became the first African nation to join the Global Plastic Action Partnership. It established the Ghana National Plastic Action Partnership under MESTI. And in March MESTI is the Ministry of Environment, Science, Technology and Innovation. In March 2022, Ghana endorsed the UN Environment Assembly resolution for a legally binding international agreement and to end plastic pollution, including the marine environment, by the end of 2024. The response work is ongoing. A citizen science approach has been encouraged. For us, the most interesting part of the NPAP is the enabling of innovation and technology transfer. Out of the NPAP has come the roadmap for radical reduction of plastic pollution in Ghana, with realistically achievable goals. I note that the Rethinking Plastics in Aotearoa New Zealand report, released by our Prime Minister's Chief Scientific Advisor in 2019, also calls for a national plastic pollution plan, but we don't have a roadmap yet. The area of the NPAP of most interest to us is the enablement of innovation and the transfer of technology. While in Ghana, I discussed our capabilities and how we can assist with the Minister of the Environment, Science, Technology and Innovation and her key directors. MESTI has a big role in implementing a plastics roadmap, and these 2 slides are from my presentation to them, giving a brief outline of our capabilities. the interesting thing from this slide in particular, I think, is that the cost of a survey specified UAV for the work that we undertake is approximately 80,000 Ghanaian cedis, about 10,000 New Zealand dollars. And basically, for the data capture that we do, a UAV of this type is not particularly unaffordable for government departments, particularly or from universities or other organizations. So our colleague Dr. Nadi Tago has already undertaken some UAV surveys at Kuligano Beach. And this is a UAV of that area. It is the beach, but also some area in the background as well. This is a view of the area that our students have taken and sent to us. Yes, so this was undertaken by students from the University of Mines and Technology and Takoradi. There was 18 to 23 millimeter resolution range, giving a minimum plastic detection size of approximately 3 centimeters squared. Waste classification was plastic and non-plastic. The initial plastic waste subclasses were plastic bottles, food wrapping, food containers, plastic bags. But there was extensive non-plastic waste classes detected, including tires and construction materials. This presented training data problems. Our algorithms had not been trained on much of the waste surveyed at this point. This is something that potentially, after the presentation, Nala can talk a little bit more about. But the current situation, as we understand it, in terms of plastic waste recycling, is that in many coastal locations, in particular, there are informal settlements of people who, as part of their scratching out a living, recycle plastic waste. This plastic waste is paid by is collected by weight. And the price varies between 1 to 3 cedis, or that was the price then, on the type of plastic that is recyclable. And while it's quite efficient, there's only the waste of value is collected and recycled. We have been discussing with Misty for using our solution to map areas of waste along the coastlines, in particular to start with anyway, and to look at a process of cleaning the beaches and cleaning the areas by the local people who are living there, and keeping the beaches clean. And the means of doing this, or the means of ensuring this is done, is from the systems that we would use. We'd do baseline surveys along each of the areas, and then after a period of time, we would go back and monitor the particular hotspot location, and we could go back and keep monitoring those at a regular basis to ensure that compliance is met. And with that, the local people would be paid the amount that was agreed between the government and themselves, or the authorities and themselves. So this is one of the applications that that can be offered by the solution that we have. It accurately surveying, but also accurately monitoring in the aftermath. I think one of the big issues is that to ensure that remediation measures are put in place, that there is an accurate method of determining what's happened before, establishing the baseline, and then comparing that baseline to the subsequent surveys used by monitoring. So this is one example. The other examples that we're looking at with this solution that can possibly be used is in the areas of oceans policy, marine debris, of course, plastic, coastal conservation and restoration, ocean governance, climate change solutions with ocean benefits. Obviously, in the waste area, phasing out single-use and non-recycled plastics. Waste management networks, helping with the establishment of more effective waste management networks, and also water, also looking at what's in the water as well as on the beaches or on the rivers or the stormwater systems. And in the area of climate change, the solution can be used to look at land use changes, as I mentioned before, to look at from a policy and regulatory perspective, establishing baselines and of a particular problem area, and looking at the policy and regulations that are required to mitigate or remediate, and then use the system to then monitor that is being done. And adaptation and resilience for vulnerable communities and countries. So there are many countries around the world, particularly in the small island development states, where sea level rise is a huge problem for them, and they, by using this technique or by using similar type of techniques, they can monitor the situation that they have themselves and help to formulate plans to mitigate some of the problems that they're facing. So we see this as a very good and basically a fairly cost-effective solution for many of the problems that we are facing as a global society, as not just plastic, but it can be used and modified for other purposes. This is the research behind the policy that we have, or the solution that we have, and it is the paper is called a deep learning model for automatic plastic mapping using UAV data, authored by two of our working group members. So thank you very much. That's really all I have at the moment, but I'm more than happy to take some questions.
Thank you so much, Mr. Simon Ironside. I think that was a very great presentation. And team, I think it's time for us to take questions. And then I'm sure a lot of questions have been asked in the chat box. So we'll take, myself and Veronica will take turn in reading them.
Okay, so the first question is, what challenges did you face in training the AI algorithms for plastic detection, especially with varying waste types?
We had a lot of problems, actually, because there were no libraries available, and there still aren't very many libraries available for plastic waste. So, as I said in the presentation, what we had to do was we had to manually classify the type of waste that we found. And that was a slow process. But as we are doing more surveys and as we are finding more, we are getting more data, we are able to then train the algorithms to recognize the different types of plastic waste that we come across. But the problem is that plastic comes in there's all different types of plastic, and we don't realize quite how ubiquitous and how it affects our daily lives. So effectively, it's the classification side of things and making sure that the algorithms can detect plastic and also the plastic type.
Okay, thank you. And the second question is, this is from Francis Andorfom. How can this process be scaled into taking into consideration the cost and work involved?
Well, I think this is quite a good cost-effective system. I think all that is needed to capture the data is a survey specification UAV. The areas can be flown. The ortho photos produced. We can either do the remote. We can either process the data using the algorithms remotely. And the cost of that is something in the order of 750 euros per site, for example, at the moment. But also, the other way of doing it is for if it's going to be over a long-term period of time, then they can be the algorithms can be used on site and locally. So we find it quite cost effective. Really, it's all that's required is a UAV that can undertake survey work and trained operators to actually capture the data, then prepare the ortho photos, which is a relatively straightforward GIS task, and then from there the data can be either remotely or locally processed.
Okay,
All right.
thank you.
We also have a question from Christian Kwesi also. It says, in the case of water samples, how do you separate microplastics from organic materials without degrading organic materials? Any proper laboratory procedures?
That's a very good question. We are not able to detect microplastics. We can detect plastic of size of 1 centimeter squared. That is with that 4 millimeter resolution that we were talking about. That is the size that we can detect. Getting down microplastics, then that's the actual plastic itself. But then microplastics then break down so that you almost can't see them. So unfortunately, once they're microplastics, they're kind of gone. So our role, and I think the goal of everybody, is to try and stop the plastics getting onto the land and into the oceans before they break down into microplastics.
Thank you.
Okay, and this question is from Blessing. She's asking, if I were to produce a plastic waste hazard map, example, to predict areas that are vulnerable to plastic waste deposition in urban cities, what methodology do you recommend?
Well, I recommend this methodology. Actually, I think what you do depends how accurately you want to find it. But in certain locations, I would suggest you could break the areas down into locations. You can undertake a UAV surveying campaign to produce the ortho photos for each of the areas that you're working in. I realize in urban areas there is quite a bit to do, but it would have to be a survey over a program of surveys. But basically, you would then prepare orthophoto base maps, if you like, of what you've got now. You would then implement the policies and implement the regulations for cleanup, for mitigation, and for clearing the waste away, putting in place policies, for example, to stop the dumping of plastic into waterways, or dumping the plastic on land, or to have waste collection services, all that sort of stuff. And then what happens after that is you would go back after a period of time and you would look at it again. And the advantage of this process is that you've got accurate mapping all the way through. So you can look very accurately at what was done, what the baseline was, and then you can go back and you can look at what what in the first monitoring survey, the second monitoring survey, the third monitoring survey, and the cost of it is relatively inexpensive, because I would assume that, for example, a government department would already own, or they could contract in a UAV and an operator. So that's really all anyone needs to actually capture the data. The data can then be processed still relatively inexpensively, and you would have accurate information to compare against.
All right,
Okay.
thank you. Veronica, please go for it.
Okay, so this question is from Mame Boafwa. She's asking, what AI or machine learning methods did you use to train your data? What's the way forward? Do you think waste separation from first end of disposal could do any better in mapping our wastes?
I think this is probably the way to go. We also looked at satellite imagery, but the problem with satellite imagery is it can cover it. Well, the advantage of satellite imagery is it can cover a wide area, but the information is not accurate enough really to do the detection and classification of the plastic or the waste that is that is being detected. This is why we then looked at UAVs, and basically then looking at smaller locations that can be covered. And really the only limitation of this system is the limitation of the UAV itself. When you're in, for example, in mangrove swamps, or you're under trees, or in areas that it's difficult to survey anyway, there is a limitation that you have with a UAV. But generally speaking, you can get a fairly accurate data that is captured, and then you can do the processing. The reason that we went with the ResUnit 50 algorithm, we tested others, but we found that the ResUnit 50 showed a stable performance to detect and classify floating plastic in the different data sets and for different spatial resolution. For underwater and floating targets, we got some very high scores, and basically we found that of the ones that we used for testing, we settled on ResUnit 50. It is also used in other GIS applications, and it can detect plastic and it can detect waste that and it doesn't need a lot of training data. Most algorithms do need to be trained. Well, they all need to be trained, but we found that the ResUnit 50 was very useful for us, because even with not particularly highly trained algorithms and a lot of data, it could actually detect and work out what it was looking at. So that's why we have gone with, we decided that we would go with that particular architecture.
Okay, thank you. I think we have another question from Ray. This is from Ray. He's asking, is the model publicly available in case one wants to use or train them in their own custom data sets?
It's research that we've undertaken. I'm not sure if it's, I mean, we'd have to talk to people about how to do it, but and how to use it. But it's research that we have undertaken ourselves. So it's not in the public domain necessarily, no.
Okay, thank you. This is from Christian. He's asking, in the case of water samples, how do we separate microplastic from organic materials without degrading organic materials?
Sorry, I
Any
think
proper
question has been
laboratory
asked
testing?
already.
Yeah, I think I
Sorry,
answered that one
Veronica.
before.
Yeah, that has
Yeah.
been asked already. So let's
Okay.
move on. This Francis Andoful again. He says, what is the practical application of this detection method? Monitor plastic or quantify plastic? And if so, what is the pollution action in this process seeking to initiate?
We're seeking to initiate. Yeah, we're not. Yeah, in this process, we're not. We can't stop the plastic, I guess. So what we're doing at this point in time is determining the extent of the problem at particular locations, and using accurate information to inform policymakers and to inform regulators of the problem that they have, and then to inform policy making, policy decisions, so that okay, we have this problem here. How do we stop it? What do we do? Let's put this work plan into play. And then afterwards, we would go back and say, we would then go and do more monitoring of that and say, yes, that was successful, that worked, or no, there is no change, or it's gotten worse. So I mean, this is only a very small part in the whole plastic pollution problem. We've got to look at the whole use, the plastic the life cycle of plastic. We've got to look at the use of plastic, and stop using as much as we do. Alternatives, we've got to look at recycling. There's a lot. I mean, it's a huge issue. But as surveyors and geospatial professionals and GIS professionals, what can we do with this? What we feel we can try and do is measure, map, survey, which is what we do, and inform, as we do with other work. So that's really the process that we see.
All right, thank you, Simon. I think there is another question here, part of which you probably have already answered in your earlier submission, but it says, this is from George Owusu. Considering the negative effects of plastic waste on the environment in Ghana, will you agree to a ban on plastic use just in the case of Rwanda? If yes, what form should it take?
I think one of the problems, yes, I mean, in theory, yes, ban it. But I think one of the attractions of plastic is that it can be quite useful. But I think there are other issues as well with Ghana, for example. Water is in plastic bottles, and those plastic bottles are recycled, thank goodness. But in order to do this, I think you have to then have a good water supply. You have to have good waste collection infrastructure, and I think there's small things that can be done all the way down the line. The government is doing a lot, I think, in recycling and trying to introduce recycling measures, to minimize the use of plastic if possible, and trying to look at alternative ways of using plastic. And it's not just in Ghana. Every country in the world is also dealing with this problem. What do we do? Do we get rid of plastic bags and use maybe paper bags, or go back to earlier more traditional technologies to, for example, for carrying, for carrying shopping and carrying things like that. So I think the whole society, there needs to be societies rethinking the use of plastic. It is, there's no question that it is useful, but the effects of it are slowly killing us. So we have got no choice, but we've got to move away from plastic as much as we possibly can, and we've got to manage the waste that is resulting from plastic. And as I said in my presentation, plastic is a very, very difficult thing to recycle. You can't it's when you burn it, it's very polluting. It doesn't break down very easily, and when it does, we get these microplastic problems. So it is a problem that needs to be addressed by all of us. I think we must have a conscious decision, in our own lives. No, I won't use that plastic bag. I'll use another method or whatever. But I think from a government point of view, banning is a good idea, but then you have to be careful of the problems that are caused by doing that as well. So I think overall it's reducing, recycling, all that stuff as well. It's a big issue, and there's a lot of policy stuff that needs to be looked at, as well as just your society attitudes and all sorts of things. So, yeah, banning is certainly banning if there's an alternative. Definitely, if there's not an alternative, then you just cause another problem.
Oh,
All right. Thank
okay.
you. Veronica.
All right. So this question is from Hayford. It
Mhm.
says, please, what type of UAV sensor or camera are we looking at to execute such tasks? RGB, multispectral sensor, and also could LiDAR data be more effective approach?
LiDAR data could be, if it's there is UAVs that use LiDAR. Again, it's a question. I mean, you could be using LiDAR to put it this way. There are litter classification standards around the world, international classification standards, and they are looking at classifications and sizes down to a centimeter squared, which is the Australian one, and then you have the UN and NOAA and all the other classifications. They are 2.5 centimeter resolution. So our solution, our research focused a lot on those litter classification standards, which are internationally accepted. I think when you go to things like LiDAR, there are LiDAR sensors that can go onto UAVs, and they will be very good too. But I think if you're using, for example, flown LiDAR, it comes down to the resolution again. It comes down to what you're actually detecting. I think one of the reasons why classification is becoming more important is, I think, institutions like the World Bank, who are getting quite serious about trying to help governments fix the problem or do something about the problem, is they want to be able to classify the plastic so that if it is for example, a Coke bottle, they would, in theory, they would then go to Coca-Cola and say, okay, this is your bottle, you're going to have to help with some of the cleanup. So I think it depends on what the actual outcome for the amount that's surveyed, or the data that's being surveyed is going to be used for. And if you're happy with a lower accuracy standard, then yeah, there are other ways of looking at it. Effectively, though, the more accurate you've got, the better chance the algorithms have of doing their detection and classification post-processing. Excuse me.
Okay, thank you. Okay, moving on to the next question. This is from Ray again. Can the study be modified to detect and track the presence and movement of large cluster plastics using high-res satellite imagery, for example?
Yes, it can. It can. As I said before, the accuracy obviously becomes less. But I think, for example, there is a lot of collections of plastic in the oceans at the moment. They are held in these they're called these gyres. They're effectively brought in there by winds and current and tide, and they're sort of sitting in certain areas in the oceans, and they're not the more densely packed, of course, the easier it is to detect from satellite imagery. But sometimes they're not quite as they're not quite as packed, and therefore even high resolution satellite imagery might not be able to detect it, or at least classify it, or whatever. But yeah, I mean, certainly it can be used. It comes back down to the actual purpose of the surveying that's being done. But the algorithms can, I think they can detect from any source of capture. It's just you'll have to modify your expectations of accuracy and classification, the less accurate they become.
All right. Thank you very much, Simon. So there's one from Ezekiel Azane. He says, are there still some unclassified plastic materials used in UAV during your classification? If so, what percentage of these materials remained unclassified?
Like I said before, there is a lot that we have still that is still unclassified, and we are still having to train the algorithms in it. We started out with very basic plastic bottle and other fairly well-known plastic types, but as I said before, there is a lot of plastic, different types of plastic, shoes, all sorts of things. So what we have to do is build up this waste classification library, and that's something that we really want to try and get done by as many people as possible, so that those libraries can then be they can be enhanced, but then they can be used for for processing and classification. And the whole idea is that you don't have to do it, a human being doesn't have to do it all the time. It starts out that way, and then as the libraries grow and the algorithms understand what it is it's looking at, then the amount of classification and the amount of human intervention becomes less. But at the moment, one of the limitations that we do have is that these waste libraries, no one's really done or has really started to look at this that seriously yet. So they're not there yet, but hopefully over time they can be built up.
Oh, all right. Thank you, Simon. So Dennis Lamte is giving a recommendation here. He says, why not introduce a token for every bottle or sachet of water sold so consumers can return it for a refund after use,
Yes.
instead of imposing a ban? So the question is, I would like to form a question out of this. What is New Zealand government doing about plastic? Or how were they able to address this issue?
They don't at the moment. They used to do it for glass bottles, beer bottles, soft drink bottles, etc. It's not done now, and in New Zealand, we are also discussing this problem, this solution of paying, for return. They do have informal. We can recycle plastic, various types, not all plastic, and we can take plastic bags and food wrappings voluntarily to the place that things were bought. But the government has not brought in a payment scheme for example, plastic bottles, and I think that's a very good idea. And I think that would be very useful for Ghana or Nigeria or any other country that's suffering this, if they want to get serious, by starting to reduce the amount of rubbish that's lying around. Yeah.
Oh, all right, thanks. A little follow-up. Is there a classic example you could share with us anywhere around the world where they actually have this menace and have been able to make a headway?
Yeah, I think there is one place that I'm aware of is Vietnam, who have a huge problem with plastics, very, very big problem with plastics, as much if not more than Ghana, I would suggest. and they are doing a lot of the whole thing about cleaning up plastic and sorting out plastic is all to do with political will. I think it's if the government are forced to address things, then they will, and if they then make a commitment to do it, then they have to. But there they are doing all sorts of things. There is a refund program, and they have a lot of they place it very high on their priorities. So therefore, they support communities to clean up areas. They're doing a big I think they're building big plastic recycling process plants, and they're doing an awful lot to clean up. And I think every country can do the same thing. It really comes down to political will, and as each of us as citizens, really, it's just making people understand, or making governments and ministers and members of parliament and politicians aware that this is a problem that we don't want. It's an intolerable problem. It's really bad, and it's causing all sorts of problems at the moment. So it has to be cleaned up. So, there's a lot, as I said before, there's a lot of work that's got to be done, right at the international and national policy levels about the amount of plastic to use, and if you're going to use plastic, can it be make sure it's recyclable and all that sort of stuff. But yeah, I think it's all about citizens in a country saying enough is enough. We must do something, and really the whole idea then is that politicians must follow the will of the wish of the people, really.
All right. Thank you. Veronica, is
Okay.
there any other question?
Yeah, there's this question from Richmond. He says he wants offline a bit, but he wants to ask if was the approach an object detection or semantic segmentation one? It is possible to compute the area or even possible the volume of the waste in the automosaic. Is it possible?
Yes. Yes. It was semantic segmentation, and yes, it is.
All right, thank you. I think that's all.
Have any
There's
more
no more
questions?
questions here.
All right.
Okay, please. There's some few questions here. There are some few questions. How do you plan to improve the classification algorithms to handle more diverse waste types? And the second question is, how does the performance of the RANSNet 50 model compare with other deep learning architectures tested? Thank you.
Okay. I think I talked about that a little bit before, but the ResUnet 50, we used used others, and I'm not sure exactly which others they were that we used. I didn't do a lot of the testing. It was done in with another colleague. But they found that the ResUnet 50 was what really worked best because it needed minimum training, or not as much training as the others, and it was more reliable than some of the others in detecting the plastic. So by having that controlled environment and knowing exactly what it was that was being looked at, we could then evaluate each of the algorithms and say, each of the architectures and say what, and look at what each had produced. And it was, we found that the ResNet 50 was the architecture that gave us the best results, was most reliable. And what we did find was that although the algorithms couldn't detect everything, we could rely on the ones that they did detect as being accurate and being correct. So that's really what we did there, as far as as using. That's why we settled on the ResNet 50 model, which is used in other GIS applications as well.
Okay, thank you very much, Mr. Ironside.
Thanks so much, Simon. So before we move on to the closing remarks, may I have your attention for the following announcement? The second annual general meeting and conference for the Ghana Geospatial Society is just about a month away. It is scheduled for 28th and 29th of November 2024. Venue is at Ghana Shippers Council in Accra. And we look forward to your participation in what promises to be an insightful event. And then there are also calls for papers. Deadline is 30th of October. So we invite researchers and professionals to submit their papers on geospatial topics related to environmental resources. There is also going to be induction. And so we are accepting applicants for application of new members to join the Ghana Geospatial Society. If you are passionate about geospatial technologies and their applications, we would love to have you on board. And the last but not least, the continuous professional development. Kindly stay tuned for upcoming CPD sessions that will help you enhance your skills and knowledge in the geospatial field. Next CPD is Geospatial Solution for Urban Planning and Development, which is going to happen tomorrow, Monday, 21st of October, 2024. Thank you so much for your attention. May we now have the remarks.
As we approach the end of our webinar, I would like to extend a heartfelt thank you to all of you for your active participation and valuable contributions today. Indeed, your engagement has made this session incredibly productive. We would also like to thank Mr. Simon Ironside for sharing his expertise and insights. Thank you. Please don't forget to mark your calendars for our upcoming second annual general meeting and conference in November. We encourage you to submit your papers by the 30th of October and consider joining the Ghana Geospatial Society to stay connected with our initiatives.
All right. Thank you once again for joining us. Stay safe and let's continue working together towards plastic-free environment. Bye-bye, everyone.
Everyone.
Thank you very much. Goodbye.